For me, it's a pleasure to introduce Victor Milenkovic as a tutorial speaker. Maybe I should say welcome back, Victor, to these cutting and packing sessions, because you were an active participant in some cutting and packing sessions back in the 90s. I didn't meet you at that moment, but I read some of your papers when I started to work on nesting problems. And as there is an increasing interest in our community on irregular packing in 2 and 3 dimensions, I think it's a very nice opportunity to have you here and for you to describe your developments on geometric computation. So it's really very nice for us to have you here, and welcome. And maybe I should say the screen is yours.
Thank you. Okay, so let me share, and this should work. Okay. I hope you don't mind. I keep my, when I give my lectures to class, I keep it on a screen on the left so I can see all of you in front of me. In fact, I'm going to expand that so I can see more of you. Okay. So the topic today is ACP, a library for robust geometric computation. I want to start off with acknowledgements, so I'm not rushed at the end. I have allowed 15 minutes of slack for questions. So if you have a question, raise your hand or type in the chat, or we can speak at the end. I'd like to acknowledge, first and foremost, Alicia Sachs of Purdue University, with whom I've been working with for many years now. Joe Masterjohn, my PhD student. Another student, Chloe Arlock, who did some of the work you'll see here. Nabil Boot, who worked with Alicia at Purdue University. Justin Stoker at UM. Steve Track, another PhD student. And of course, the National Science Foundation, which has funded most of this work. So the outline of this talk is that I'm going to talk first about what I've been doing lately, which means since I last presented at ESICUP. And so they're going to talk about a review of work in robotics and packing, and 3D, and rotation, and 4 degrees of freedom, and the lessons that we've learned from that. That will include a review of computational geometry, adaptive control perturbation, and something concept that we discovered, identities. And then I'm going to go over an ACP library we have created that takes care of doing the things you need to do so you don't have to relearn the lessons that we learned. And then, of course, thanks. So let's go back to the 90s, perhaps. This is a lesson that I have in my computational geometry class, where I asked the students to take here's an obstacle for a robot, and here's a robot, and calculate the boundary between the object overlapping and not overlapping the obstacle, and that's this red boundary. And the robot can only translate in X and Y, so it has only 2 degrees of freedom. So the free space is 2-dimensional, and so you can overlay the free space onto the space itself. So the complement of the free space, so the free space is all the world plus this island, and the complement is the block space. So as long as the center of the robot stays outside the block space, it doesn't overlap the obstacle. And mathematicians call this the Minkowski sum, and in packing, this was the famous no-fit polygon from the 90s. And really the difference between packing and path planning is that for path planning, you would say, oh, the robot can't get inside. But for packing, you would say, oh, look, there's a little island, a little hole in the no-fit polygon, so I can't actually pack this one polygon inside the other. So this can be generalized to 3 dimensions. So the Minkowski sum is simply for A, Minkowski sum B is A plus B for A and B and B. And we developed an efficient algorithm for polyhedra. And so here are some nice polyhedral shapes: frame, knot, torus, dragon, helix, bull, inner ear, horse, so forth. and Minkowski sum. So here, for instance, the horse Minkowski sum with the sphere gives us a somewhat dumpy horse. The knot plus the dragon gives a, I don't know, a very knotted dragon. So very interesting shapes we can do. So this, we can do Minkowski sums of polyhedra. And so there's some old packing work done. You want to pack 3 polygons into a box. And this is work back in '87 by Avnem and Wassenat. Let's call the polygons P1, P2, and P3, and call the complement of the box P0 for technical reasons. And so we're repacking, the box itself is a complement of P0. And it makes the formula simpler. So if you do that, then you do the Minkowski sum. So you can see these are the complements of no-fit polygons. And then you do some intersections and some Minkowski sums, and some more Minkowski sums, and some more intersections, and you get a set. If that's empty, there is no way to put the 3 into the box by translation. If it's not empty, then you pick a point and you do a translation, another intersection, another translation, and another intersections, and another Minkowski sum. Pick another point, another translation intersection, pick another point, and in the end you get T1 and T2 and T3, which are translations of the 3 polygons that will place them inside the box. The rectangle, it could be a rectangle or a parallelogram. So this is not our work, this is Avnem and Wassenat. But the point is that once you have intersections and specifically Minkowski sums of polyhedra, then you can apply this to polyhedra. So you can pack 3 polyhedra by translation into a box. And if it can be done, it does it. If it can't be done, it doesn't. And it could be as irregular as you want. But this is somewhat unnatural. For a clothing manufacturer, for instance, you might say you don't rotate because of the grain of the fabric. But it's a little hard to imagine why you wouldn't be able to rotate these shapes a little bit. So one of the things we looked into was adding rotation. So if you have a robot, such as this sort of a racer-shaped robot right here, and an obstacle, which is the outside of these 2 rooms and corridor, and you allow the robot to rotate, then the shape of the free space for the robot depends on the orientation of the robot. So here, for instance, the robot has this orientation, and this is the shape of the free space. As long as the center of the robot is within the green region, then it's not over, it's within the within the rooms or the corridor and not intersecting exterior. We rotate the robot this way, we get a different shape, and you can see it's extending a little bit into the corridor, but we know this is a false hope because the robot is badly oriented. It could go into the corridor a little bit, but then it will get stuck. It needs to be rotated 180 to sort of turn and slide through the corridor. But this motion, the motion that's required is both a rotation and a translation. So what we can do is we can stack up all these green shapes and get that shape. So that is all the green shapes for all the orientation of the robot stacked up into the 3rd dimension. And this is actually continuous in angle. So this is definitely algebraic. These are algebraic surfaces. And you can see at a glance that it's possible for the robot to get from one room to the other because you see this narrow corridor which corresponds to in the free space, which corresponds to the robot rotating and translating to get from one room to the other room. So this, in a sense, is the rotational no-fit shape. It's not a polygon anymore. We have a nice video on YouTube for it, and I guess I could possibly share these slides at the end. So that's fine. And what about 3 dimensions? Because we're talking about 3 dimensions. Well, the fact is that if the robot is confined to the plane, such as an old style Dalek, it can go in X, it can go in Y, and it can rotate. So it still has only 3 degrees of freedom, just like this that robot I was showing you. And so the shape of the free space looks somewhat the same. In our case, of course, Daleks are not polyhedra, but we can do it for polyhedra. So given a polyhedral robot and a polyhedral obstacle, we can calculate this no-fit shape, this block space and free space, and it looks something like this. and we can do path planning. And also this means that if you have a container and you have a shape that you want to put in the container, and you have to keep the shape upright, so it's not allowed to tilt. So it has 2 degrees of freedom to go into the container, and you can rotate. Then we can use this to decide whether or not that's possible. But also to plan a path to get inside, in or out. So you can place it in the container, or we can even figure out whether you can get it into the container, assemble it. What about adding another degree of freedom? So as followers of Doctor Who know that at some point, the Daleks got the ability to fly. And so that gives them a 4th degree of freedom. That is the Z direction, up. Now, for the most part, the Daleks didn't fly like Superman with their heads forward. They kept their heads upwards. They just sort of floated around like drones. So like a drone, a typical drone has to hold up using helicopter blades. So it has to remain upright. So it has the freedom of X, Y, Z, or it can rotate around its Z axis. So that's 4 degrees of freedom. And we do that. The drone free space, I can't show you the 4-dimensional free space because we can't see in 4 dimensions, but I can show you some paths that we can generate. And so for instance, here is the robot inside. The drone is inside this room, and the room has a corridor to another room, and then that room has a window to or a door to the outside. And so it has to figure out that it needs to navigate the robot to the corridor, then turn and go out the window. And so we have this video here which shows the 3 rooms. Here's the first room, here's the second room, here's the outside. And so when I play it, you see the robot going through the corridor into the second room, then turning and going through the door to the outside. And this, so we are traversing, finding a shortest path with maximal clearance in the free space. Now, here's another example where the robot is kind of a cross-shaped drone, and it's trying to get past these very thin pillars while it goes up a ramp. And whoops, that is right here. And so we can see the robot in action. So we can do this 4 degree of freedom navigation. Now the thing I have to admit to you though is that whereas we have worked on the continuous angle problem, this actually slices the angle into intervals so that it's an approximate solution. And so it just makes really heavy use of the polyhedral Minkowski sum. So we can lots and lots of Minkowski sums to generate the sort of the free space in multiple layers. So perhaps I could show you the free space after all, because I would just show you this many 3-dimensional slices. So we did that work. There's other work, but that was the most, I think, relevant to cutting and packing. And what I want to talk about now is the lessons we learned from that work, in particular, the numerical lessons that we learned. So first of all, I want to review what makes a computational geometry algorithm. So computational geometry algorithms branch on predicates, which are determined by the signs of polynomials on the coordinates. So one typical predicate is turn P1, P2, P3, which can be written as P2 minus P1 cross P3 P minus P1, but this is a 2-dimensional cross product. So it's a scalar. It's just simply x2 minus x1 times y3 minus y1, x2 minus x1 times x3 minus x1, where x1 and y1 are the coordinates of P1, and so forth. So the thing is about this particular quantity is that if it's positive, then it means that going from P1 to P3 is a left turn. If it's negative, that means going from P1 to P2 to P3 is a right turn. And if it's 0, that means that P1, P2, and P3 are collinear. So this is something you need to know in order to go ahead and do things like, constructing. So as we will see. So just to give an example of how you use the turn, here is a pair of line segments, AB and CD. And another thing you do in algorithms besides calculating predicates is you calculate new points. So you calculate new coordinates. And so what you first do is you say, hey, ACD is a left turn. So that turn is positive, but BCD is a right turn. That turn is negative. And so turn ACD times turn BCD, that's less than 0. And that tells us that A and B are on opposite sides of line CD. And similarly, turn CAB times turn DAB is less than 0, which tells us that C and D are on opposite sides of line AB. And that tells us that the two line segments intersect. So therefore, there must be this point P. And so it's safe to calculate it. You wouldn't want to calculate it if the two line segments were parallel, for instance. So you can calculate the intersection. And it's a rational function, and it uses cross products and so forth. So it's A plus something times B minus A, and that scalar is a ratio of two cross products. But the point is that it's a rational function of your original inputs. So that's sort of what computational geometry is about, is evaluating predicates to make decisions, and then once you've made the decision, using them to calculating new points or other quantities, planes, what have you. So the lessons we learned, kind of a hard-fought lesson for us way back when, was that one should use interval arithmetic. Interval arithmetic, for instance, if you have, well, let's imagine that instead of using double precision arithmetic, which gives you 16 digits of accuracy, you're using a floating point which has only 2 digits of accuracy. So if you multiply 1.5 times 1.7, you get 2.55, but that's necessarily rounded. So it can be rounded down to 2.5 or up to 2.6. So the trick with interval arithmetic is to do both and to create an interval. And that way you know that the actual value is somewhere within this interval between 2.5 and 2.6. And then if you continue from there and use these intervals, let's say we multiply 1.3, 1.4 times 2.7, 2.8, we exactly would get 3.51, 3.92. But again, those can't be represented. So we round, but the point is that we round the first one downward and we round the second one upward. So we get 3.5, 4.0, and we know whatever number is in this interval and is in this interval, it's the product of those two numbers are definitely in this interval. Well, so what? Well, remember, we need to know the signs of predicates. And the one thing you can tell about this interval, whatever number that is, you don't know what the number is, but you know it's between 3.5 and 4.0. So therefore, it's definitely positive. And that's just what you need to know for computational geometry, that something's positive or negative. So we know the sign. Now, what if the interval contains 0? Well, one thing you can do is use more precision. Like here, I was only using 2 digits. Of course, with double precision, you got 16 digits, but sometimes that's not even enough. And so you can use software floating point, so a lovely package, MPFR. So you can use more. And doing that is a little hard to program, and it needs a support library to sort of recalculate. You don't want to recalculate everything. You just want to recalculate the things that you need to recalculate in order to do that predicate. But that's the basic idea. But the problem is that this does not work for 0 predicates, which is to say, if you have 3 collinear points, then it's 0. The value is 0. And so therefore, the interval will always contain 0 because it always contains the correct value. But no matter how much precision you use, you don't know if maybe you use just a little bit more precision, you would get 0 out of the interval. So you just don't know. Is it always containing 0 because it actually is 0, or just because it's very near to 0? So the trick we used for that was to say, well, take the input and randomly perturb the input a little bit. When I say a little bit, I say by 10 to the minus 8. Now, 10 to the minus 8 is negligible for practical applications. you know, there's no manufacturing that has more than like 6 digits of tolerance. You know, I mean, I guess if you were making, you know, Elon Musk might want something higher for his spaceships, but I'll tell you, not for his Teslas. So it's negligible for practical applications. And what's interesting is that even though you're taking something that's 0 and then you're making it slightly non-zero, so you think the interval would likely contain 0, that double precision is 16 digits of accuracy, and we are only perturbing 8 of those digits. And so most of the time, double precision is still plenty good enough, and you don't need to use MPFR very much. And so the overall running time doesn't increase by more than 20% from using MPFR. So we call this adaptive controlled perturbation. And it is based on something older called controlled perturbation that did a large enough perturbation to guarantee that the predicate could be calculated in double precision. But sometimes that required a non-negligible perturbation, bigger than was practical. So we said, oh no, let's use a fixed perturbation of 10 to the minus 8, which is negligible, and then use additional precision when necessary. And it turns out that that works great and doesn't increases running time maybe 20%. So we thought we were sitting pretty. We thought, okay, we got this solved. We can go and do all the geometry we want. Then we started having an identity crisis. And what do I mean by that? Well, first of all, detecting 0 is impossible for interval arithmetic. Well, okay. I don't want to get into the math of it. Eventually, if the interval is small enough, then there is ways of saying, oh, it's got to be 0, but some things called root separation bounds. But those are so pessimistic that if you use them, you would have to be really grinding a lot, spending a lot of time in MPFR. And there are other approaches such as exact irrational arithmetic or exact integer arithmetic, but they're also expensive. So you say, okay, but you got rid of zeros because you perturbed the input. Your points are no longer collinear. Not necessarily. So here, consider this example where we have the red polygon and the blue polygon, and we intersect, and we get this shape, okay? And this shape, hey, how about that, has got P1, P2, P3, P4 that are collinear. And the reason they're collinear is because they are all lying on the original line segment AB. So actually they're collinear, and no matter how much you perturb A, B, C, D, E, F, G, and H, they will remain collinear, okay? Because they all lie on line segment AB. So if then what you do is you want to construct a convex hull, or in the class I'm teaching, if this is like sort of a hole in a shape, I would ask them to triangulate the outside. There's no way to avoid needing to know the value of turn P1, P2, P3. The algorithm is going to ask it. And that is 0. So now we're in trouble because we can't use interval arithmetic. And we call this predicate an identity because it is identically 0 as a rational function of the input. If you took the whole messy formula and plugged it into the other messy formula and did a whole bunch of algebra, it would all end up getting 0 in the end. It would all just vanish. And so the lesson 4 for us was that identities happen. So we thought, well, you know, it's not so hard. If you, what you should do before calculating turn P1, P2, 3, you should check to see if P1, P2, P3 were actually elements of the same line segment. So you keep track of where things come from, and you say, hey, you know, they're all the result of intersecting AB with a different line segment. So therefore, they're collinear. So don't calculate turn P1, P2, 3. It's definitely 0. But the problem is that the number of types of identity grows exponentially with the number of operations. So if you're talking about that algorithm, remember that algorithm that Avnem and Boissonat came up with back in '87 with all those steps of intersections and Minkowski sums and translations and all that. You remember that slide? Implementing that for polyhedra, Alicia spent at least a month, possibly more, writing ad hoc code, you know, to say, oh, well, if it's like this, then it must be 0. Or if it's like this, it must be 0. And it's very difficult because you tend to overgeneralize and undergeneralize, and it's a real mess. And in the end, you don't really know if your program is correct. So we needed, this is the identity crisis. We needed some way of dealing with that. So that gave us the two more insights, the two more lessons. The one lesson is that if everything's rational, so you're doing plus, minus, times, divide, so all the numbers are rational, you can do plus, minus, times, divide modulo a prime. Now, you're probably aware you can multiply, add, subtract, and multiply modulo a prime. You can also divide modulo a prime. Every number except for 0 modulo a prime has a multiplicative inverse. So you can do the whole calculation modulo a prime. And so if we take two random 31-bit primes, such as I'm showing here, it will be definitely 0 if it is 0. And what if you get 0 modulo those two primes? Well, it's going to be very likely to be 0. But what are the odds that you pick a random prime and the thing just happens to be out of all the possible moduli? It's not 0, but of all the possible moduli, it came out to 0 for this one and this one. And these are both in the order of 2 billion. So the chances that it's coincidentally 0 is something like 1 out of 4 billion. And if you 1 out of 4 billion billion. And if you're not happy with that, throw in another prime, and then it's 1 out of 8 billion billion billion. So at some point, it's so certain that you say, okay, that's fine. Now, there's a little bit more to the story, but empirically that we have tested, and that it turns out to be true. And what's nice about this approach is that it also detects degeneracies. You don't have to perturb the input. There's no input perturbation required. To get rid of degeneracies, you just do, if you have an interval which contains 0, you do this modular test, and you can tell, oh yeah, it actually should contain 0 because it actually is 0 with very, very high probability. Now, for algebraic expressions, things are a little more difficult. There is a way we worked out to use this trick to deal with algebraic expressions, but in general, it's very difficult because whereas there are reciprocals, multiplicative inverses modulo a prime, there aren't necessarily square roots or roots of polynomials. So you can't do the algebraic computation modulo a prime. So what you have to do is construct a residue field which does have the roots, and that gets kind of expensive and messy. So we took a different approach for that. We went back to perturbing the input to get rid of ordinary degeneracies. So the only time it's 0 is if it's identically 0. And then we would say, well, if it's identically 0, then even if you use like 200 bits of precision, the interval will still contain 0. And even if you take the inputs and perturb them, again, it will still contain 0. And so the point is that, and then we worked out the statistics of it to show that, yeah, that it's very, very unlikely, very extremely unlikely that it isn't 0, but you're being fooled. And so that's the approach for algebraic. So overall, these are the 7 lessons we had, and it would be a little difficult for you to apply these 7 lessons in your work, and so that's why I talk about the third part of this talk, which is the library we created. So the library really should be called ACP. Remember, ACP is adaptive controlled perturbation, but also PD, probabilistic degeneracy detection, which is what I was just talking about. You either use modular arithmetic, modular a couple primes, or you do some random perturbations, and you can be sure that things which look 0 actually are 0. And that way you don't have to do interval arithmetics on 0 quantities. And so the library has this one weird trick, the design trick, that you have to put up with if you use it. And that is when you create a geometric object or a predicate class, you have to provide a no argument calculate method. And that's templated on a number type. Well, templating on a number type is kind of obvious. You need to deal with different number types. But this notion that you have to do it without allowing any arguments is a little funny. And it forces you to either store pointers of the antecedent geometric objects in the class or otherwise have a way of accessing them. And how you do it is up to you. But if we force you to do that, then when the library needs to recalculate with, for instance, more precision in MPFR, or with modular arithmetic, or with a perturbation of the input, it can do so, because it can just call your calculate method and you take care of gathering up the antecedents. So the library takes care of lessons 1 through 7, and so you do have to put up with the one weird trick, but thanks to that, you don't have to redo lessons 1 through 7. You just write your algorithms just as simple as possible. So to start off with, we provide a PV2 datum, which is a 2D point or vector templated by a number type. Okay, yeah, you have to do something like this in order to do things. So, but it's actually pretty straightforward. I hope there's some C++ programmers out there. So you have a template. It's templated by a number type, which you call capital N, and then otherwise it's pretty obvious. So if it's a 2D pointer vector, it's got an X and Y, which are of type N, and it's got a constructor which takes an X and Y of type N as arguments and initializes the X and Y of the class to those values. Okay. We do this class for you, but sometimes you need to create classes like this. It has to provide a size method to say how many numbers it stores, and a way of accessing them as if it were an array. And then finally, you need to be able to construct a PV2 of n off of a PV2 of m. So you need to be able to convert number types, but it's usually very straightforward. You just initialize X and Y off the numbers of the other type, because the number types know how to convert to each other. And so after that, you do your usual vector point operations. So for instance, you have PV2 operator plus, which takes another PV2 and just returns a PV2 with the sum of the X's and the sum of the Y's, which is obvious, adding points and vectors, and say multiplying by scalars, and then also the dot and cross product and so forth. And then the thing is that you don't really use this directly. What you use is an object of PV2. This is an object is a template that we give you, and you can just call that a point. And when an object of PV2 is something which knows how to calculate itself with a no argument calculate method, like I said. Before we get to that, let's just look at what the predicate looks like. So you remember that we had that turn predicate, and for technical reasons, we have to call it a primitive. So it's the turn primitive, that's really the turn predicate. And here's its calculate method. So the calculate method, like I said, has to be templated by a number type and have no arguments. And so what you do is you go and you get you have your ABC points, you go and get their PV2s of n. Okay, you get their point vector with that number type. And then you just simply return BB minus AA dot cross CC minus AA. So it's just very simple. Go get their PV2s and do the calculation, which is what I showed you on the earlier slide. And then because of the no argument aspect of the calculate, you're forced to write a constructor which takes the 3 points as arguments and stores the 3 points in class variables, like right here. And then if you do so, then using it is just as I showed you. You just say if turn ABC greater than 0, no problem. Now you may say, where is the greater than operator? Well, you're derived from primitive. Primitive takes care of that for you. Okay, so you just have to do this, and then you could just use it as a ordinary predicate. And then the other kind of thing we were talking about is creating new geometric objects. So you have this intersection of AB and CD. So this is what it would look like. Once again, the calculate method can have no arguments, and it's templated by the number class. And in this case, it's returning a PV2 of n. It's saying, okay, we're creating a new point, so we're creating a new PV2, and whatever the number type is, you've got to create one of that number type. And then you go through and you get the PV2 of n's, the points for that number class, and you do the calculation, which I showed you in the earlier slide, basically straightforward here, if you remember that calculation, and return it. And that's what you have to do. And then the thing is, because the one weird trick that the calculate method can't have any arguments, you're forced to have the constructor take the 4 points as arguments and store them. And we provide a smart pointer class for you. So because it's chances are when you create the intersection of two line segments, you're probably going to want to keep it around. You're going to use it. And so we use it. We provide this pointer template, which is ref counted garbage collection. Okay, so you don't have to worry about that. And so now you have all that. And so you can do the example. Here, for instance, we need to create some input points. And I did very simple input points. 0, 0, 1, 1, 1, 0, 0, 1. But in general, you would assume that you have data in a file, which is in double precision format, and you would just put the numbers you read from the file into that, and you would create PV2s of double, which is to say points or vectors with double precision coordinates. And then you would create points from those, and you would store them and save them and also use reference counts. So you don't have to worry about the garbage collection. You never have to do delete. Okay, that's taken care of for you. And there's a one weird parameter here, this false here. Well, that's because if everything is rational, then you don't need to do perturbation. So you say false. But if you're going to be doing algebraic computations, like I said, with the algebraic computations, we have to perturb the input a little bit to get rid of input degeneracy, so you would set these for true. So you have to make a decision. Is this going to be algebraic or just purely rational? So then you do the computation, just like I said. Here we're creating the intersection point P, if you remember that. And we just say turn ACBD equals turn BCD less than 0. Remember, if A and B are on opposite sides of CD, and if C and D are on opposite sides of AB, then you just create a new line intersection of ABCD and store it in P. And then go from there. Then you can do things with P and so forth. And so when you do that example with the P1, P2, P3 that were collinear, it'll work fine. You'll have these different P's. And when you do the, if it's rational, it'll just say, oh, wait a minute, this interval contains 0. That's strange. Let's do it in modular arithmetic. It'll call your no argument calculate method with the modular arithmetic n and determine, oh, that's 0 modulo this giant prime, and it's 0 modulo this giant prime. So gosh, it's pretty much certain it's 0. So let's just call it 0. And so off you go, and you can do all these wonderful things. And of course, we have the code. You might be just interested in the Minkowski sum or some of this other code, so you can let me know that too. So in any case, I don't want to get too much in detail. It's basically, that's the basics. Obviously, there's some more details. But I do want to thank Dr. Bennell for inviting me. And of course, my coworkers I acknowledged at the beginning. And if you're interested, you can send email to me, bjm@miami.edu. And we're setting up a GitHub at Robust Geometric Computation is the name of the public GitHub. And I hope you find something out of this useful, if in terms of creating your own algorithms or maybe using some of the ones that we have created. The very nice thing is that unlike other approaches, because we have this identity, we've solved our identity crisis. That means that unlike other approaches, you can combine different algorithms together, like that odd name algorithm. And the running time won't all of a sudden go to some huge value because it's spending all its time trying to figure out zeros. The running time, zeros makes no mind. You can do whatever you want and take things which are fast individually and put them together into something that's fast as a combination. So that's it. Let me see how I'm doing. Okay, doing pretty good for time.
Okay, thank you for your very nice presentation. There is some time for questions now. Please raise your hand and. Yes, Julia.
Thank you. So thank you for that presentation, and it just really does take me back to, you know, when you're dealing with this computational geometry and you find that sometimes it's these problems of trying to identify that precision and where's that zero that is really challenging. But if I could sort of go back to the initial part of the talk to around the 3D geometry and ask around how you sort of model the original shapes. So are you dealing with these in terms of just modeling the surface of the shape using some kind of, you know, mesh, or is it some other way that you're actually representing the shapes and then working from those? Because I guess implicit in that, then you have some kind of approximation that you're working with.
So we're using boundary evaluation, right? So the, as I say, the CG, what I went to is like points and then intersecting line segments. And so when in the two dimension, these polygons would be represented by XY points. And then you would just have a list of XY points saying, okay, it's this list of XY points, this list of XY points. In 3 dimensions, you would, in 3 dimensions, yeah, it's all points. You have the points with X, Y, Z, obviously, and then you link them up into triangles. And so generally it's a triangular mesh.
Yeah, yeah. And we did a project on 3-dimensional, and we looked at the triangular mesh. We also looked at voxels. So you've actually got the kind of inside as well as the surface in different ways of approximating it. And I think whether there's any efficiencies that you looked at where you could use different size triangles in the mesh in order to represent different surfaces. So you could end up using multiple triangles over a certain surface in order, because other areas of the polytope is quite, or of the object is quite intricate. So you want to use great accuracy there, but you don't need the accuracy elsewhere.
Well, we didn't do some, well, okay. A couple of things I'll mention. First of all, one piece of work that I didn't mention was that when you're doing these calculations, you can end up with some very tiny triangles or very short edges, especially like doing that name-like algorithm. And we have work on simplifying it. So, but that would be where you have an idea of what your accuracy is. You have some epsilon, you say, well, it should be that accuracy. And then we go through and get rid of triangles which are smaller than that. Either we collapse them, or if it's not possible, topologically collapse them, and then we spread them out. In that case, it actually uses a sort of a optimization. It actually uses linear programming to spread out the triangles. So we have that work, which I didn't talk about here, but that's rounding polyhedra to a certain accuracy. And then the other thing I should mention is that the 4 degree of freedom approximate work, which Chloe did, not only does she take the slice for all these different angles, but she also does approximations for different clearances. So that means that what happens is the drone tries to use the least approximate path until it gets stuck. Then it uses a finer approximation until it has one that will allow it to go through the corridor. So the coarse approximation may not even have this opening in the configuration space. And then it uses a finer approximation until it finds one that lets it go through. And so the result is you get a kind of a natural motion, whereas often for robotics, you get an unnatural motion where the thing slams against the wall and it's sort of scraping along the wall. You wouldn't want a car parking system that parked in your garage by sort of feeling its way in, scraping the side of your garage and the wall. So you want to keep yourself as far as possible. And that's done by multiple levels of approximation, sort of like what you're speaking.
Okay, thank you.
Mm-hmm. Thank you. Jose Fernando?
Good afternoon, Victor. Very nice to see you again after all these years. And I also was taken back to the 90s, to the very beginning of the 90s, when I was implementing my own library and computing the no-fit polygons and facing all these problems of the zero. That's really a challenge. But of course, that's what you have done is completely professional. Congratulations, very nice talk. But my question was regarding convexity. I don't think I have quite understood how you deal with the lack of convexity. I recall your earlier work, and you were even working with some special non-convex shapes like the star-shaped pieces, and you could treat them directly. But here, apparently, you are using only triangles. You are decomposing all non-convex shapes into triangles. I did not get them.
Well, so here, for instance, you can see these shapes are these are non-convex shapes, right?
Yeah, but they are triangulation, so that they are composed by.
So for instance, these shapes you see here
Yeah.
are represented by a triangular mesh, which is a standard representation. If you want to represent the shape of a horse, you do enough triangles so that you get an accurate enough shape of the horse. One of the aspects of graphics is you can use Phong shading, so even if the triangles are a little largish, you can smooth it out to the human eye. But so basically, these inputs were from we took it from graphics, from the graphics community. So they're fairly fine triangular approximations, and you can see obviously the horse is non-convex. Of course, every triangle that the horse is made out of, I don't think I can't, hang on a second. Here we go. So every triangle that the horse is made of is of course a convex triangle, but you can see you're connecting all these triangles together and making, a very non-convex horse out of it, which is typical.
So yes, it's a composition. It's composition in a triangular mesh. Okay, thank you.
Yeah, but it is a boundary representation, not a voxel representation. Yeah.
Mm-hmm. Okay, any other questions? Carlos?
Hello. So, yeah, you said that you took some shapes from the graphics community, and I wanted to ask, because my limited experience with that was that a lot of the times the shapes were not correct, that some triangles do not join together, you don't know what's inside, what's outside. So, I mean, could you work with them? Because for me, it was a real challenge. I thought that was really difficult to do.
Yeah, I probably have Alicia somewhere in the listening in, but there's that's actually a nice way area you can use the Minkowski sum, because if there are little crevices and so forth, you can take the Minkowski sum of the shapes. Oh, there is Alicia. I see. Alicia, how did you deal with cracks in the models?
Cracks in the models.
Like were these models, were they perfect? Or I thought you had trouble where sometimes you'd get these models and there would be little gaps in the triangulations.
That certainly happened. Was it all of, let me think a moment.
So I recall that the solution is that you take the Minkowski sum of the boundary itself. So you fatten the boundary itself by a little bit, and then the triangles run into each other, and then you take the outer boundary of that.
Yeah, I certainly did that in some cases. At one point, there was prior work by people, I don't remember the names, but MIT and Columbia, who were claiming to take these models and fix them automatically. But I didn't really find that their algorithm was convincing. There's some things that are easy to find, like dangling edges, but coplanar edges are not so good, or just if you have a significant gap in your model, how do you know how to fill it in? That was the question. So these models did not have big gaps. They might have been non-manifold, but there's big gaps. So adding a little sphere, and a little box, and a little diamond, and then taking the outer shell would work fine for these things.
Yeah, so it's a nice other application of the Minkowski sum, that you take the triangles. There's no problem. You can take the Minkowski sum of a triangle with a box, and you get sort of a fattened triangle. And as long as that box you're adding is a little bit bigger than whatever gaps there are, then everything runs into each other and it seals all the holes. And then you just take the outer boundary of everything.
Okay,
so
that's a good trick. That's a good trick. Sorry, if I may.
Because it doesn't make the model much bigger either, because the complexity of the piece we're adding is small. I'm going to mute myself again now.
Thanks, Alicia. That was Alicia.
You're welcome. Now I'm really unmuting again.
Thank you, sorry, and just a follow-up question. So more or less, how long does it take these Minkowski sums? Because if you were thinking to do a packing algorithm with this, I mean, it could have to be, you'd be doing this quite often. So do you think it's practical to use these models for, in terms of a packing algorithm?
Well, it depends what you want to do, but I mean, this is just minutes. For these kind of models, we're talking minutes. Okay, it's not. In fact, that was a thing that we had anecdotally experienced, that somebody went and took and tried to put together modules from like Segal, cutting things into convex pieces, taking Minkowski sums of convex pieces, and then taking the union of those convex things. And what happens when you do that is you get a huge number of identities, because if you think about it, you're cutting things and you're creating two shapes which have common vertices, and then you're adding them together, and now you've got lots and lots of common vertices and coplanar faces and lots of zeros, predicates. And then so the whole thing just bogs down. And I know, so Alicia indicated you talked to some company which they really needed it, and coincidentally what I believe they were doing was in fact taking triangulations and filling in gaps in triangulations using the Minkowski sum. And they were having to run the thing overnight in the cloud. But our Minkowski sum are pretty fast. And we have, as you can see, we also do it on the GPU. So, I mean, you can look at the running times in the paper, whether you find they're good enough or not. But I think we pretty much as fast as we can.
Yeah, no, if it's minutes, sounds okay. All right, thank you very much. Very nice talk.
Thanks.
Okay, any other questions? Julia?
Yeah, thank you. Sorry, just to follow up on the rotations, because I think even in 2 dimensions, this is an area that we haven't really, in cutting and packing, got our head around well. And obviously using a Minkowski sum or the no-fit polygon, whichever way you want to talk about, even in 2 dimensions, you have to reproduce that Minkowski sum for every sort of orientation, and as you said, you've had to take slices from it. You can't do it continuously. So in the example
But we do it continuously, except for the 4 degree of freedom one. This one is continuous.
Oh, okay. Right. So this is sort of looking at moving a robot through a pathway, and this is the feasible path. But I guess when we're packing, we're looking at the interaction of shapes upon shapes upon shapes, because it's how, and I think the only way I can imagine doing that is almost every time you've got a partial construction of a layout, that you then have to look at that Minkowski sum of the different orientations among the shapes that are already statically packed. I don't know whether you've sort of looked at how you can generate this complete kind of freedom of movement space, but with multiple objects.
Yeah, it's something we could look into, but it's always better if you can do the continual thing. So the complexity, this thing is see, I have the video queued up, and let me see if I can. Show you that the number of elements you have to deal with. Okay, there you go.
Processing is required to actually render it on screen. For interactive graphics,
hang on a second.
the standard approach is to processing is
okay. So you can see that the shapes are essentially triangular, except they're triangular patches of curved surface. Okay, so it actually keeps the complexity down. As you can see, the complexity is not so bad. It's just that these aren't planar pieces. These are non-planar triangles that are pieces of a algebraic surface, but the polynomial description of those surfaces is also relatively simple. So there is hope that you can basically take things that you're doing for the translational case and do the same things for the rotational case. But as I say, we haven't pushed that as far as maybe we should have. So this is something, yeah, I'd be definitely interested in looking into.
Thank you.
Okay. Any other question? No. So thanks again, Victor. Has been a wonderful presentation and very, very inspiring for many people in the cutting and packing community. So thanks again. And that
Okay, and I
closes
hope
the
that
session.
Julia can provide the slides or something. I'd be happy to
Oh, good,
provide
good.
them.
That would
Very
be
good.
great.
So
In fact, Victor, if you're happy, we've been recording the session, and we
Yeah.
would ask your permission to put it up onto the website so we can follow the whole talk.
Absolutely.
Thank you.
okay. So that's the end of the session for today. See you tomorrow.
Thank you. Bye-bye.
Bye. Bye, Victor. Thanks again.
Right. Thank you.
Bye-bye.